chair flips are not actually flips. You're not actually flipping the molecule like a pancake. Cyclohexane chair flips can be often misunderstood by students. What actually is a chair flip and how do we do it? Let's talk about it. The first thing to say when we do a cyclohexane chair flip is that chair flips are not actually flips. You're not actually flipping the molecule like a pancake. We're not taking carbon 1 and flipping the molecule like a pancake. This does not become carbon 1 in the new chair structure. When we do the chair flip, we're not actually flipping it like a pancake. It's actually a conformational isomer. We are only rotating around double bonds to move from one structure to the other. If you're not sure about conformational isomers, I have another video down below about different types of isomers. So if it's not actually a pancake flip, what is a chair flip? I made a cool animation for you. In fact, I've got another video down below where it's just this animation, full screen. You can just watch it over and over and over and over and over again so you can really figure out what chair flips are. In a chair flip, there are a couple of rules that we follow from drawing one chair flip to the next chair flip. The first is that corner carbons remain the corner carbons. What do I mean by that? That's probably not a term that your instructor really uses. It's kind of one I made up. I've got another video down below about all my terms and definitions in cyclohexane chair flips. This is also not a tutorial about how to draw individual chair structures. I've got a different video on that linked down below. This is just about chair flips. What do I mean by corner carbons? If we look at the 6 carbons of the cyclohexane, the 2 furthest out carbons, I call these the corner carbons. So this is carbon 1, this is carbon 4. The corner carbons here are also dotted. Those are also the corner carbons in the new chair flip. These are what I call the corner carbons. The corner carbons stay the corner carbons. So this corner carbon on the left side of the molecule, carbon 1, is still going to be corner carbon number 1 on the left side of the new chair flip. Same thing with corner carbon number 4. It's still going to be corner carbon number 4 in the new chair flip. What we do when we do chair flips is we take carbon 1 and we rotate it up, and carbon 4 and rotate it down. Take carbon 1 and rotate it up, carbon 4 and rotate it down. We can see that in the animation up here. Here we got carbon 1 and we're rotating it up, and carbon 4 and rotating it down and back and forth. Rotating carbon 1 and rotating it up, carbon 4 and rotating it down. That's what's happening with the cyclohexane chair flip. So what are the consequences of drawing the other chair flip then? Once we have identified the corner carbons 1 and 4, we always number the molecule in the same direction. Here I've numbered the circle clockwise, so we're going to number the ring clockwise here as well. This is still carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. The corner carbons remain the same and the numbering remains the same. That's how we do a cyclohexane chair flip. The next thing to keep in mind, all of the groups stay in their respective northern and southern hemispheres. What do I mean by that? If you look at this cyclohexane, this orange bond, whatever it is in the northern hemisphere of this molecule. I have a whole other video on treating the cyclohexane like a globe. It's a really important way of thinking about cyclohexanes, and I've got that one linked down below as well. This orange group is a northern hemisphere group. This red group is a southern hemisphere group. This red group is a northern hemisphere group. This orange group is a southern hemisphere group. That's what I mean by northern and southern hemisphere. When we draw a chair flip, everything in the northern hemisphere has to stay in the northern hemisphere. Everything in the southern hemisphere has to stay in the southern hemisphere. What happens when we do that is that all of the equatorial groups become axial groups, and all of the axial groups become equatorial groups. When we do the cyclohexane chair flip, everything that was equatorial becomes axial, everything that was axial becomes equatorial, but it stays in the same northern or southern hemisphere. I think this is one of the reasons that cyclohexanes are so confusing for students, because we've got all these terms and definitions and they don't have a one-to-one correlation. Wedges, dashes, northern hemisphere, southern hemisphere, equatorial, axial, they all mean something with chair structures, but they don't have a one-to-one correlation. Something that's a wedge in one structure is equatorial in one chair structure, but axial in another, and it gets a little bit confusing. That's okay. Take your time, watch the animation, figure out how this works, get it right. You can do this. I'm here to help you. When we draw the chair flip then, once we've identified the corner carbons, we look at this orange group. It's in a northern hemisphere equatorial group. It has to stay northern hemisphere, but now it's going to become an axial group. The axial bond on carbon number 1 is axial straight up. Again, if you want to learn about how to put the bonds in the right place, I've got a different video on that down below. The red bond on carbon 1 is a southern hemisphere axial bond, so it will be a southern hemisphere equatorial bond in the new chair structure. The red bond on carbon 4 is a northern hemisphere axial bond, so it will stay a northern hemisphere bond, but become an equatorial bond in the new chair structure. The carbon 4 equatorial bond is in the southern hemisphere, or will stay in the southern hemisphere, and now become an axial bond in the new chair structure. This is how we think about what a chair flip is and how we draw the different chair orientations of a molecule. Here's another chair structure we can do together as a worked example. Pause the video first, see if you can draw the other chair structure for this given chair structure. First, let's apply a numbering system. Doesn't matter how you number it. I always like to make the left corner carbon carbon number 1, and I like to number clockwise. That way I don't have to think about my numbering system. Corner carbons have to stay the same. If carbon number 1 is the left corner carbon in this chair structure, it has to be the left corner carbon in this chair structure, and I'm still going to number clockwise around the ring. Everything that's in the northern hemisphere stays in the northern hemisphere. So this bromine on carbon number 1 is in the northern hemisphere. Right now it's an equatorial group, so in the new chair structure it will become a northern hemisphere axial group on carbon number 1. That would be this bromine here. Carbon number 2 has a northern hemisphere OH group, so that means it will stay a northern hemisphere but become an equatorial group. The equatorial group points towards the corner carbon it's closest to. Again, that's in another video I have linked down below. So the OH group becomes a northern hemisphere equatorial group. The CH3 group is in the northern hemisphere axial on carbon 4, so it'll be northern hemisphere equatorial on carbon 4 in the new chair structure. And on carbon 3, I have a southern hemisphere chlorine. It will stay southern hemisphere. It was axial, now it is equatorial. This is how we can take one chair structure and convert it into the other chair structure using this northern-southern hemisphere method. These are the tools you need to take one chair structure and convert it into its equivalent chair flip.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.